All right, hello everyone, and thank you for joining us today. My name is Jordan Larsen, and I work at NASA Marshall Space Flight Center, and I will be your moderator for the Advanced Solid-State Metal Additive and Extrusion Technology webinar. As part of my role at the NASA Technology Transfer Office, I work with NASA scientists who have developed new technologies that may have applications outside of the aerospace industry. Our presenters today are Dr. Josef Cobb and Zach Courtright. Dr. Josef Cobb is a weld mechanical engineer for NASA. He specializes in solid-state joining and additive processes. He has led qualifications and risk reduction efforts for friction stir welding processes on NASA's Space Launch System and other flight projects. He is currently running several joint R&D projects with NASA and other commercial vendors regarding friction stir welding and friction stir deposition processes. Dr. Cobb is also involved in alloy development projects for both the friction stir deposition processes and high entropy alloys for 3D printing. He holds a PhD in mechanical engineering from Mississippi State University and is a licensed professional engineer in the state of Alabama. Zach Courtright has been serving as in-space manufacturing portfolio manager at NASA Marshall Space Flight Center for the past year. Previously, he worked for 8 years as a welding engineer for NASA. During this time at NASA, he's performed technical and project management responsibilities by proposing, supporting, and leading an array of research and development projects involving welding, additive manufacturing, electronics, non-destructive evaluation, and recycling. Recently, he's participated in and led projects pertaining to the development of in-space laser welding and on-demand manufacturing of electronics. He holds a bachelor's and a master's degree in welding engineering and is currently in a part-time pursuit of his PhD in material science and engineering. Before we get started, I'd just like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we will answer them during the Q&A session at the end. All right, at this point, I'm going to turn it over to you, Dr. Cobb.
Hey, thanks, Jordan. All right, so I looked in the chat, and some of you know, and some of you don't. But all right, for those of you I don't, my name is Josef Cobb. As Jordan said, I'm a weld/mechanical here at Marshall. Here, Zach and I are here excited today to talk to you about some friction stir deposition, friction stir extrusion processes that we've been working on at Marshall, and show you what the technologies are, our state of development, and where we're going with them. So just a presentation overview. We'll talk about just the technology from kind of a high standpoint, or a high overview, and the advantages of it, right? And then we'll get into the different technologies. It's a suite of technologies. They're all fed by the same feeder, which is kind of the high dollar part of the process, while the end effectors are much more affordable, although the whole process is really affordable. Talk about our ongoing work. So we're implementing currently on our bigger and larger friction stir welding systems. We've got some academic collaborations going on, and then talk about future work on where we want to go with the technology. So from just an overview perspective, NASA's developed a novel advanced solid-state additive system, or what we call NASA processes. Little pun on NASA there, but they allow the incorporation of friction stir deposition and friction stir extrusion processes into traditional friction stir welding machinery. So that's kind of a big point of this, is that you don't have to buy an entire machine like you would with a meld system or something like that, right? This is an end effector that bolts on and off. And so we're like, just for instance, we're changing out, I'm getting a little ahead of myself here, but we're changing out from friction stir welding to friction stir deposition in 10 minutes. You know, we can go from one to the other just by bolting on the end effectors and the feeder, and then just unbolting it, and we're right back to a friction stir welder. So there's 3 different types of technologies. So there's 3 different ones. We've got what we call conventional friction stir deposition. It uses a pin that's similar to conventional friction stir welding. It's not milled, but has like a conventional pin in it. Then we've got a bobbin and also self-reacting friction stir deposition process, and then a friction stir extrusion process. So advantages over traditional friction stir deposition. The end effector model allows for rapid transition, like I was saying earlier, in really just minutes, from friction stir welding to friction stir deposition and vice versa. You can convert your existing friction stir welding machinery. And if you have large scale friction stir welding machinery, you can do large scale friction stir deposition just with the end effector. And the end effector can go on any of those machines, right? You just need to build an adapter plate to bolt it to, and you can go on any friction stir welding machine that you have. We get near net shape and net shape parts when we're done. So we get a smooth as built surface. So we don't have the surface quality issues you'd have with meld where you need to machine a 1/4 inch off, and that picture on the front, it just won't die, right? So we've got some much better depositions than that. And then for the extrusion side of things, infinite length extrusions. So let's jump right in and talk about the different technologies and how they work. We'll start with the conventional friction stir deposition. And so this is a lot of pictures, and it's hopefully we'll explain it through here without having to ask questions. I guess one thing is, can y'all see my mouse just to make sure?
Yes, I can.
Okay, sweet. So the process, we'll start down here in the bottom right-hand corner. So this is actually what sets the shape of your deposition for the conventional friction stir deposition. So you can see here's a die, which is in reference to the model of what's with the feeder and everything on it right here. It's this green part on both sides of the deposited material. And we're feeding in a feedstock. So in this case, we're using a square feedstock that we're feeding into. There's a pin that comes down here in the center that's rotating. And this image on the right is actually the first deposition we made with this process, and our feed rod got stuck. So we've made quite a few improvements there. But the feed rod coming in, you can see where the pin was stirring and what kind of deposited material comes out the backside. So I just thought that this kind of lays out kind of what's happening real well. We're pushing in a feedstock into the stir zone. We're just ramming it in there. This is stirring, plastically deforming the material, heating it up, right? And it's taking the shape of the opening on the backside. So between those two things, this is actually what this machine right here, a 3D model of it. So you can see for this current iteration, we're using a ramrod system where we feed run 1 12-inch bar at a time in through here. It gets rammed inside of there and it gets deposited down onto our plate that's running on this table right here. So, I put these videos in backwards. Yeah, let me jump a few slides here. Well, I guess I put the same video in twice. Sorry, fellas, I had a video of the process going, but I guess I uploaded the same video twice for some reason. It got jumbled up. I guess I didn't save it. But here is what that deposition looks like when you get done with the process. So this is as deposited, a 1/4 inch by 1/4 inch material deposition. And so this is as deposited. We get a really smooth surface finish. So there's no carbon in our deposition. We did have carbon previously, but we have since removed the carbon from the process. So it's just an as deposited. This is a 2195 deposition onto a 2050 plate. So I think we've kind of touched on some of these advantages here, right? But we've got a modular design that bolts on in minutes. So it's a low cost investment, right? It's really the cost of the feeder. And we'll talk about the continuous feeder and what that looks like, where we're going with that later on, right? But the end effector's not very expensive. You know, we're talking like $3,000–4,000 to get that machined and made up, right? And then you've got your feed system, but compared to the friction stir welding machine, right, a really low cost add-on. It gives additional capabilities to what you've already got on there. If you have a friction stir welding machine, we're not removing a capability, so you don't need additional floor space. You don't need additional machinery. We've got an extruded surface finish when we're done. It's a really smooth. This is a really zoomed in image, and we can do a wide range of print geometry. So this is a square opening, but we haven't demonstrated it yet. We're installing our process on one of our new machines, our PDS machines here. But we intend to print stiffeners directly onto skins, so squares or whatever, and you can print multiple passes, one on top of the other, to build up walls and things of that nature. Here's some macros of the process. So this is what just a cutaway of that looks like. And you can see this is a 6061 deposition right here. And this was one of our earlier ones where we were using carbon on our feed carbon coated rods to help with the sticking issues that we had initially. And you can see how this carbon kind of becomes entrained in here. But really good solid joining all the way through here. You can see where the pin extends down into the metal here. And then you can see some more carbon right here on some of the banding. We got rid of that and we went to the 2195 rods. And so you can see here, this is a 2195 onto a 2050 plate, but we get good adhesion, a really refined grain structure the whole way around. So we don't have those issues with any of the processes that we're talking about here that you typically see with like a meld, where you're worried about joint quality, especially to like a base plate, right? Where you're worrying about that. We really bust up the oxide layers because we've got that pin driving down in there. So if you've got a harder material and you want to put a softer material on there, or vice versa, right? We really get good working of that metal and stirring all the way through our interface joint. So really good, really nice bonds with this particular process. And that's kind of an overview of the conventional friction stir deposition. Zach, I'm going to turn it over to you and let you talk about the Bobbin friction stir deposition.
Awesome. Thank you. Thank you, Joseph. And yeah, before I get into this, I definitely want to re-emphasize that the reason why we call these the Novel Advanced Solid-State Additive processes, or NASSA processes, as a suite of processes is because they're directly interchangeable. So each of these, like the Conventional Friction Stir Deposition, Bobbin Friction Stir Deposition, and Conventional Friction Stir Extrusion, are all just end effectors. So they can just be bolted into place. And like Joseph said, it's really only a 10-minute changeover, either from one of these end effectors back to a friction stir welding machine, or from one of these end effectors to another end effector. So you could be doing all of this with the same machine with very minimal changeover time. And I think one advantage, one additional advantage beyond what Joseph mentioned, is that just insane deposition rates. I know you could see it in the sample that was shown, but yeah, that the filler material is a 1/4 inch by 1/4 inch filler material. But with the conventional friction stir, there was I think it was a 625 height by 1/2 inch width stiffener in a single pass. So it's, I mean, just astronomical deposition rates that are unmatched by any other process.
And those deposition rates, right, don't require machining post deposition, right? So it's all usable material, and you save those steps.
Yeah, you don't have to deal with a bunch of waste, and similar to meld, you can, like anything that can be made with friction stir welding, it's conducive to these processes as well, like with respect to materials, or the ability to modify the feed mechanism to feed in different types of feedstock rather than just rod, but maybe chips or other things too. Next slide, please. So yeah, this is an overview image of the proof of concept lab setup. We demonstrated this technology. It was probably 1.5 years ago when we first successfully demonstrated the capability. We've got it confidently at a technology readiness level 4, if any of you are familiar with that scale, which is basically a proof of concept in a lab. And basically this is a ramrod feed mechanism, like Joseph mentioned. And as you go into the drawing, or into the image, just below the pin tool is where this containment mechanism exists to contain and drive the material into the plate. Next slide, please. So this design here shown on the right is like way over designed, because we wanted to make sure that this was going to work. So we made sure to be extra redundant, and because, you know, there's different loads that are occurring in all different directions, and we were using a machine that was more of that wasn't really designed to handle these kinds of loads and everything. So we wanted to add a ton of extra redundancy, which ultimately most of that was not necessary, and we found that out. So going from that image on the right to the image on the left, you can kind of see a greatly reduced amount of intricacy for the tool. But basically the way that this works is the feedstock travels in from the left side of this picture on the right, through this green part here, into a containment block, and then through that containment block into the stir zone between the like a standard bobbin or self-reacting friction stir tool. So it feeds right into that stir zone. And then what's not shown here in this image would be a plate that would be clamped in place, kind of where Joseph's pointer is there, or like where he showed in that image on the bottom left. It could be part of a dome or something like that. So basically the tool rides along about, you know, right now we proved about one, like it's 7/8 of the tool is engaging into the plate or the prior layers, and then 1/8 of it is where the is not engaging, but it's actually where the filler material is coming in and where it's being stirred in. So basically, with every pass, it is stirring. In this configuration, like I said, it'd be about an 1/8 inch per pass, and the pin tool was a 1 inch diameter. So for every single pass, you would be stirring seven of the prior passes, and in addition to one new pass. So it's kind of mixing that all in. So you get really good adherence to prior passes. So that's something that just at a lab scale, we were able to demonstrate that with an 1/8 inch deposition. So that's already an order of magnitude greater than pretty much anything else out there. But that was just lab scale. So theoretically, you could get to the point where your deposition is at least half of the diameter of the pin tool, which for a 1 inch pin tool would be a 1/2 inch per pass. So there's definitely a lot of potential to increase that further. But again, like Joseph said, the surface finish is very smooth. So you get basically kind of like a friction stir finish along the whole surface of the print, and it would not require any form of machining. You could either it's kind of similar to some undulations you may see in certain additive processes where you get a little bit of surface roughness, I would call it, because it's kind of like the stir zone or the top surface of, like I said, a friction stir weld. But you can easily, if you wanted to, remove that with Scotch-Brite pads. But in my opinion, it really isn't necessary to modify that at all. So it's essentially print in the net shape as built condition, ready to go. So yeah, so that's it's kind of hard to see exactly what's going on here, and I know there's a video a little bit later, so that might help to make it a little bit more clear. But next slide, please. Okay, so this helps to elucidate it a little bit more. So that brown piece would be a filler material rod coming in through any number of different feed mechanism styles, but this was a ram rod. And then basically the pin tool, the plate, or it could be a dome or a cylinder or really a number of different shapes. Basically, the tool rides along the side of that. And for the initial start, you may start off with a notch to be able to make it easier to contain the initial material. But depending on how much you're depositing with each pass, that may not actually be necessary. But like I said, we were being extra conservative in the initial depositions and proof of concept. And I had these green bearings were designed in place to help with redundancy, to make it so the containment plate doesn't like twist or torque, because that type of thing we had noticed in the past could lead to the pin tool kind of gouging into the surface, or part of the containment plate gouging into the surface, and ultimately leading to limiting out the machine. But with this redundancy, we were able to get rid of that. But ultimately, there was one primary redundancy point, and that was actually bolting the entire containment mechanism to a rigid block that is adhered to the actual, like, to the machine outside of the spindle. And by doing that, we were able to essentially eliminate any amount of torque or movement that could happen in the containment plate, and that essentially eliminated that issue. And yeah, as you would go, you deposit this material. This filler rod would come in, the tool rotate and stir that material into the prior layers or the start plate, and then it would travel along to the right. And as you can see, like, that tool direction is to the right, and it would deposit material up to, like, for this, an 1/8 inch, but like I said, up to about half the diameter of the pin tool is very reasonably feasible. Next slide, please. Before we show the video, I did want to mention that because it's a Bobbin Friction Stir type deposition, it can also be used for self-reacting tools. So if you have that secondary axis with a self-reacting tool, you could actually open and close to be able to increase the thickness of the deposition. So say you were building a cylinder, or you're building like a stage or a cylinder or a pipeline or something like that. You could be depositing at a monolithic thickness, but then once you get up to a point where you want to have a little bit more stiffness or you have more stress concentrations, you could thicken that area over a number of passes, and then essentially have kind of like a built-in stiffening capability. So that's one of the interesting advantages. And then also, if you're familiar with self-reacting friction stir welding in general, one of the big advantages is being able to go around complex curvatures and basically deposit things like cylinders and domes, or you could do like sinusoidal joints or different shapes depending on the needs that you have. But yeah, now that I've gotten through that, we can show this video. It makes it a little bit more clear. So yeah, the tool is feeding into the screen right now. The plate on the left is rigidly fixed, and the filler material is coming in through the containment, through that feed mechanism and into the containment mechanism and into the stir zone, and all as the tool is feeding into the plate. So that's kind of how the filler, the ramrod mechanism works. It's just slowly feeding it in. And then this is a sped up video of showing the deposition. So that start piece, if you're familiar with friction stir welding, it's typical to have a start block or something like that would be cut off later. If you were moving in a continuous fashion, you wouldn't have that issue. So basically this whole steady state region that you're seeing right there is what it looks like. And that plate is as built. You can rub your fingers across it without getting a splinter, but there is a small amount of flash there that's inherent to a self-reacting type process. So that's something that you could easily remove with just a Scotch-Brite pad, or theoretically you could just run back over it and it could be reconsumed into the next pass. But in general, that getting that flash down to a very low level is something that's just common to development for friction stir processes, where you optimize the parameters to get the flash to the lowest level possible. So that's like I said, not something that would require any amount of post machining. It's pretty easy to get off. But yeah, that's Bobbin Friction Stir Deposition. And I mean, like I said, it kind of fits. Okay, so there's another slide. Sorry. Yeah, so
Actually, Zach, I put in a few more slides. I put in the metallography and stuff here too.
Oh, you did? Yeah. Okay, cool. Thank you. Yeah, so like Joseph said, I mean, these processes are really interchangeable. And the fact is, like, the investment, the cost, like we just went to mom and pop machine shop down the road and we're able to get them to build end effectors for us. And these end effectors were, I mean, like Joseph said, $3-4 grand at most. Like, I mean, that's really including the cost of the bearings that you would have to put in there. So they're definitely really low cost, and you can modify them. And like, we've designed a couple of different methods to allow some modularity. So you could not have to buy a whole new end effector, but just, replace one part of the end effector to increase the thickness or the deposition heights and things like that. Yeah, and we designed everything to use the same feed mechanism for all three of these processes. So the ramrod feed mechanism has been used in the past, but Joseph will talk more about a continuous feed mechanism that's about to be up and running right now. And let's see what else. Yeah, so like I said, dome, cylinders, all kinds of different things. So this image on the right kind of shows how beyond a dome, it could be used to actually print the flange as well. So you can imagine where that little blue piece is sticking off the left, that's where the filler material would come in. And then you've got your spindle coming down from the top in blue. And then that containment mechanism basically just contains and drives the material into the prior passes to make that monolithic surface. And then there's a couple images of like this image in the center here shows a plate before pass and after pass. So you can see that's an extra, like it's a plate that hasn't been deposited onto next to a plate that has. So you can see the 1/8 inch difference in height with a single pass. Next slide, please. And then, yeah, so we took one of these, and this one is as built. So with this one, we were able to get the flash down pretty significantly to where there's essentially nothing and if there is, it's something that you can just like use your fingers and wiggle off very easily. So definitely not a huge concern. But yeah, so we took this plate and cut it up and did some metallography and some hardness testing. So this is like the metallography of my dreams right here. It's the most beautiful image I've ever seen when it comes to macros. Not biased at all, of course. But yeah, so you can see on the left here on this image on the bottom that all those ripples right there show how this material is being fed in and stirred in. And really only so you can kind of see where the grain refinement goes back to like a rolled condition on the right. So that's like the nugget starts there and goes to the end. So that's like 1 inch, that whole area. So that area where the filler material is being mixed in it goes well beyond the 1/8 inch deposition. So where Joseph's pointer is, that's about as far as the actual deposition height goes. But then as you can see, it's stirring back into at least the last few layers. So that really helps to show like where that filler material is going. And yeah, we were also able to do all of this without any use of carbon. So that was really valuable. And we added a taper to the inside of our feed mechanism to enable feeding without jamming up without carbon. So that's a really big advantage as well. And then the next slide shows a micro hardness map that we did, which basically aligns with what you would expect to see, pretty similar material property drop that you would see in any friction stir weld. So as you work to optimize, it's completely reasonable to assume that you could achieve 60 to 80% properties of like what the original material was. But that's that kind of brings me to the point where some of this would require, like, depending on the alloy, if you're familiar with friction stir welding, some would require some amount of post build heat treatment to get you back up to certain properties if you wanted specific properties. But there's also kind of a revolution of new alloys that are being released specifically for additive processes that do not require quite the level of post processing to get to the properties. But in general, I mean, the amount of, rather than having to take a large sheet, cut like an isogrid structure into it, bump form it into a shape, and then weld that together into a cylinder, and then weld a dome onto it, or have a ring forging that takes 2 years of backlog to make and has 95% of it get machined away to get to the final product. You can theoretically use these types of processes, these friction stir deposition type processes, to do all of that in a much more streamlined fashion, similar to how some other additive processes are used. And now I'll transfer it back over to Joseph to continue on friction stir extrusion.
Yeah, and Zach, if I could, just a few more things on kind of properties and stuff like that, right? So this is an 1/8 inch, right? And Rev 2 should be, 1/2 inch when we put that on our new machine here. And then we're already doing, 1/2 inch build heights, and we're going to be going to 3/4 inch and beyond that on the conventional depositions with the new stuff. But some of the advantages you get with that too are also, with your meld processes, right? Your 1 to 2 millimeter type deal, right? So there's a ton of layers to build up, right? So there's a lot of thermal cycling, a lot more time at temperature associated with that. And so with these processes, we're expecting to get a lot less distortion post build, and a lot less grain growth, right? Because we won't be reheating that material over and over and over again every pass. We're going to be jumping, a 1/2 inch or an inch at a time with each layer that we print, right? So it's only going to see one thermal cycle, whereas your other processes, you're seeing 10 thermal cycles, right? So that'll be, I think, a large advantage when you start going to really big parts, right? When you start talking about tall, big, large parts, there's a lot of potential there to just reduce that thermal cycling.
Yeah, that brought me, that actually, you talking about distortion actually reminded me of the concept of, like, if you're talking about a meld process and you want to build up, say, a cylinder or something like that, you're eventually going to get to a height where you start kind of mushrooming and like forging the prior layers, and it won't be able to support itself. So one of the big advantages of this Bobbin friction stir approach is that similar to like Bobbin friction stir welding, you don't have to have, a lot of those loads are being reacted by the tool itself. So there's nowhere near as much load going down into the part. So the amount of height and the minimum thicknesses that you could achieve and stuff is a little bit more robust.
Yeah, for both the processes, right? You don't have that force of the rod being driven into the part that's being printed, right? That's all being done by the tool itself. And so you just have the force, of a tool, whether it's the pin or the two shoulders, right? That's all you've got, and they've got containment to help hold that in place. So much different there. All right, so then friction stir extrusion. So this is the one that this is a if you think about conventional friction stir deposition process, it's extrusion on 3 sides, right? We get a really smooth extruded surface finish when we print that. And this is just taking that 4th side where we were welding to our base plate or our previous deposition and just making it into a die also. And so then we just get what we call a friction stir extrusion. So we can make parts. We've got feed rod coming in. The pin is redistributing, plastically deforming this stuff, right? And then it's to the opening shape of whatever you want to come out. So full disclosure, we haven't built this system yet. It's part of the suites, and it's our next in line to build. And once we get the continuous feeder up and running, we just felt like it, based on what we'd already done with conventional friction stir deposition, and just the transition here of just adding a bottom piece to it. We've just been waiting to get the continuous feeder where we can feed in and make long extrusions with it, and just learning what we can from the conventional friction stir deposition. But similar feedstock, or similar feeder to the C-FSD and B-FSD. That's a typo there. But feed rod comes in through the hole here. There's a little bit of a cavity right here, but between the pin, right, and get some bearings holding it on both places. It stirs it, plastically deforms it, and redistributes it through here. And some of the nice things, I guess, about it from a single rod feed system is, your pressure, your inlet pressure is set, by this square geometry, and then your pin is redistributing it. So you can get much larger extrusions without having to go to larger and larger forces with that. And I've got another chart over here just to kind of show this a little bit different with the feed rod coming in, right? You can kind of see the cavity in the pin down through there, right? And it getting stirred up. And then you just cut whatever shape you want in here. You split this in half, right? And so you just bolt on a new front face for whatever it is that you want to print, right? You just grab the new face and just bolt it on there, and you'll be able to print each time you go. If you want a different shape, a different geometry, right? You just need to cut a new front piece. You can do infinite length extrusions. And for this one, right, you can bolt it onto your friction stir welder, but also you don't technically have to have a friction stir welder. You can just have a motor to drive this, right? And so then you can have an extrusion machine that just sits wherever, and it's a modular thing. Actually, we're looking at using this for recycling, in-space recycling, right? So that's a big thing. We can just make our own little standalone feeder to make either feedstock for other additive systems, construction materials, just recycling all the materials that we have in space for whatever needs we may have. And that's the friction stir extrusion kind of in a nutshell for a single pin. But what really gets interesting is, because we don't have the increase in die forces, right? We're just feeding in this and the pin's redistributing it, right? We get all our pressure from just the force go of that pin going in there. You can take this process and you can have multiple pins, right? So in this process, right, these back pins are getting the material first, right? So we're creating an extrusion, and we've cut this particular die geometry in this example right here, right? So we're going to extrude our stiffeners in here too, right? As long as they're covered by the deposition of the pin, right, in that area, we can make whatever shape we want to. And this is going to extrude into essentially these two pins, which are also rotating, right? And then we get a fully extruded closed structure at the end. And so all we need to do is just have more continuous feed systems. And this is an old image with an older, early, just kind of concept design of a continuous feed system. But essentially, right, you just need more and more feed systems, continuous feed systems. You don't have to go up to these 1 million pound presses, 10 million pound presses if you want to get really large diameters and really large geometries. You're just using the pin to rotate it, and you just have multiple feeders going into it. So if you've got one of the continuous feeders, you can do this with it, right? If you get more of them, you can do larger and larger parts. But essentially, you only need the motors, right? So and you can make really whatever shape you want to. You just have to have a rotating pin kind of going through that geometry to make it. But I would like to grow this kind of from just a NASA perspective, right? I'd like to grow it out and make my pipe dream is to have extrude the entire core stage tank in one single shot, right? Have a bunch of feeders, and in a different presentation, I've gone through and done the math on what that takes. It's actually not too unreasonable to do that, and where you could make the whole tank, which currently takes us, weeks and months to make. There's a bunch of different welds and a bunch of different panels going in there. And this process would be something that could extrude that in, 4 hours is kind of the target time frame for extruding an 120-foot long extrusion at that size, right? 115 feeders. But that's that's the gist of the large scale extrusion process, the multi-pin extrusion. Something we're actively looking forward to making and working on here in just a few weeks. So next steps, whatever, that's kind of this, what we've shown you is where we are, what we've done. And so here's what kind of a breakdown into where we're going to next. So we're going to, the machine we were on previously to do all of this work was a machine that we were about to access. It was, it was a blessing because no one cared about the machine. So we were able to do whatever we wanted to with it. But there was also a reason that no one cared about that machine. And so it's not a very rigid machine, not a lot of load and torque capability. And it doesn't allow us to record any forced feedback data. So we don't get any feedback data from that machine in a file that we can put together. So what we're doing now is integrating the processes. We built a continuous feeder. So this is built, and we're doing the final assembly of it today, actually. And we'll be integrating that into our process development system here at Marshall. And so that's a much more robust friction stir welding machine, really accurate, a lot larger build volume. We'll be on a 4 foot by 6 foot by 3 foot type build volume. And so right now with the processes, we're doing about 6 pounds an hour on that other machine. We're significantly upping our deposition sizes there. And so we're targeting 50 plus an hour. I don't think it'll be hard to hit 20 pounds an hour. I think that should be just straight out of the box. But it's going to allow us to have much higher deposition rates, do continuous prints. So right now, if you saw the C-FSD one, that was essentially our rod. When I chopped off the start and end of it, that was 1 feed rod's worth of width there, or worth of length there. And then with the other process, since we were only depositing the 1/8 inch at a time, right, we could run that plate. But once we start going up to the larger and larger deposition widths on these B-FSD, then we're going to need the continuous feeder to also be able to make longer and longer prints. So we've done that here. We've also started adding some active cooling, right? So there'll be a liquid cooled end effector on the end of these, right, to deal with the heat that we'll have coming from the longer deposition rates. But all that stuff's getting put on the PDS this week, and we should hopefully at the end of this week start making depositions with this new setup here. And then that'll allow us to do the multi deposition prints, right, one on top of the other, because we can get the length to make those depositions. And then we'll start doing the design allowables and initial qualification builds for some of the parts that we've got here in-house that we want to start building. And then we've got some interest from commercial partners to start looking at doing some parts that they're interested in as well. And that's the end of the presentation from a technical point. I think Jordan or someone was going to talk about licensing, I believe.
Yeah, that was me. Thank you guys. That was an excellent presentation. I do have a couple slides that I wanted to go over on the licensing aspect before we jump into Q&A. So right here, this is an image of what our technology transfer portal looks like online. We have over 1,200 different patents that are available to be licensed out. When you get to our website, which is technology.nassa.gov, you can search our 1,200 patents either by keyword or by category. We have 15 different categories, as you see here. We got stuff in health and medicine, sensors, materials, coatings, all kinds of really great stuff. Once you get to each page, there will be different buttons where you can ask us questions to apply for a license, or you can reach out to our licensing concierge, and he can help guide you to the correct center to answer any questions you might have about a specific technology. On the next slide, you can see an overview of our licensing process. Our team here is available to help you every step of the way. We are working to ensure a seamless experience while addressing any questions that you might have. We have a couple different licenses that are available for you guys. We have an evaluation license, which is what we typically suggest people to start off with. They are $2,500 and they last a year. And it's a great way to test drive the technology, see if it's a good fit for your company. If it is, then we suggest moving over to a commercial license. These commercial licenses are available in exclusive, non-exclusive, or partially exclusive. Each license is completely negotiable. There are no set terms or fees associated with those. They're completely negotiable, and will be set upon that negotiation process. Next slide. Here, we're going to leave this page up for you guys. These are the different technologies that we've been talking about in this webinar. And after this, we're going to jump to the Q&A. Feel free to scan these QR codes if you'd like to look at our TOPS pages that will link you straight to our website during the presentation. Okay, all right, so first question. What ambient conditions require T and P?
Sorry, what ambient conditions require T and P?
T and P, yes.
Ooh.
Temperature and pressure is what there were.
Oh, okay, what ambient conditions? So solid state, right? We should be able to do this process at really any temperature and pressure, right? So currently we've done everything at, standard temperature pressure, right? Just room temperature pressure, right? We've got a climate controlled environment we're working in. But I don't know which environment you're looking for. If you're looking for like an in-space environment, we think that right, we can sit. One of the big benefits about solid state deposition, right? If you're looking for an in-space, lunar, Martian, whatever you're looking for, is that it's gravity insensitive, right? So whether we're at 1 G, 0 G's, lunar, Martian, or whatever G's we're at, right? We're insensitive to that, and that allows us to simulate essentially all the key process variables here on Earth, right? Which will be really important when it comes time to if you need to do process development and have a high degree of confidence that it's going to work where you're going. And then also if you have any non-conformances or things you want to evaluate, you can do those evaluations here terrestrially as opposed to whatever location you may want to be at doing those. And all of it's transferable. You can do all that testing prior to getting there, and then also, while you're there, if you need to run a bunch of stuff to try and evaluate, some non-conformance or something of that nature, which we do quite often here at NASA. So I hope that answers your question. But everything that we've done currently has just been at standard temperature pressure.
Okay, thank you. If a commercial company were to license this technology, what do you expect it would take for them to take this licensed patent to final commercial product? Like, do you have a time range or?
So we're getting this on our PDS system, which is a PAR machine currently, right? So PAR's coming in. They were coming in this week, but some stuff that we had getting done to the parts got delayed, so they're coming in the week after Thanksgiving. But once we put this on here with the commercial system, right, and see how that runs, if everything goes well, it really shouldn't be long to commercialization, right? I think several of the friction stir welding OEMs have expressed interest in, making this as a product you can buy from them, right? So they can, have that technology as an add-on to their machines, right? That's already integrated in there. So just purely because it's the PAR machine we're going to, right? PAR's going to make the software upgrades, right, to integrate this in where it's all done. So depending on how the feed system works, which we haven't tried that yet, but we have a pretty high degree of confidence that that's going to work well, or just take some minor modifications to get it working properly. I don't think it will be that long. We hope to be making multi-wall depositions in early, end of this week, early part of December, right? Nothing's going to happen at a government facility on the week of Thanksgiving, but yeah, that's, in 2 weeks, right? Time frame. We expect to be making multi-wall prints where we can start assessing the allowables, and the stuff we've done so far, looks like we're in, friction stir welding, that 70% of parent material print, parent material depositions for a T8 condition, which is kind of what we use all the time. But I would think it would be fairly soon, not some far off thing. We're fixing to implement the stuff that we think will take us to making commercial size parts. So then it's just testing after that.
Excellent. All right, thank you. Can European companies license? I can answer that one. The answer is technically yes. It is just a very lengthy process. We have to get a federal register notice that's approved by headquarters. It takes months and months and months to get it approved. If you do have a U.S. subsidiary, it makes it a lot easier. We would suggest applying for a license through that U.S. company, and then it would make the process a lot easier. Another part too of that is a lot of our patents don't have protection worldwide. They're only protected here in the US, which is something that we consider. So the answer is yes, but it just gets tricky. All right, next question. What deliverables, technical documentation, or knowledge transfer support would be available to licensees of this technology beyond the patent itself? I'll answer part of that and then I can jump over to you guys. So with a license, what you're guaranteed is the ability to practice the patent. Anything beyond that is something that we are offering with good faith. Most technologies that we have offer some sort of technical data package or something of that nature to help people get started, because we do want to see companies that are licensing our technology succeed. So if we have something available, we do want to share it. As far as inventor support, typically what we do is once a license has been approved and signed and executed, we do a kickoff meeting with the inventor and the company, and within which we will go through the technical data package if available. Then we give them a while to digest it, and then we have another meeting set up where we can go through and answer any questions. After that, maybe one more meeting. If you're wanting something a little more in-depth than that, that depends on inventor time, and we'll probably be moving into more of a reimbursable Space Act agreement to compensate them, because you have to remember that these inventors, they have full-time jobs here to support NASA. Tech transfer is just a side quest that they do to help benefit the country. And with that, do you guys have a technical data package, or what kind of information do you think you would be able to provide to companies?
So we haven't put together a technical data package yet, right? We've kind of been working on getting the continuous feeder down, right, where we can make our long depositions and stuff. But I would definitely think there would be helping work with the companies, right? We're working with friction stir welding OEMs, right, to implement this on their equipment, right? Because obviously they want to have an extra, I won't say widget, but they want to have an extra technology, right, to help with the machine, selling their machine, right, and with the customers out there who already have their machines, right, as an add-on bonus feature, right? So there's a lot of interest on that standpoint, right? And so that'll be coming down the pipe there. And then also we're also working with academics. So we're working with BYU out in the Center for Friction Stir Processing, and they're doing some process evaluation and stuff like that. So there'll definitely be help out there and stuff available, right, as this stuff goes on. But I don't have a technical data package put together yet, but I imagine that would be something in the future once the continuous feed system gets built and starts depositing stuff. And kind of finalize what the design is to print, commercial parts.
Excellent, thank you. All right, next question. You presented results for AI alloys. Do you think that these can be used for high temperature materials like Ni alloys, Ti alloys, refractory alloys? Might need higher temps, tools, materials, example.
Yeah, so the physics of it are friction stir welding physics, right? So the limitations of it are also similar to friction stir welding limitations, right? So if you want to go to those higher temp materials, you're going to need to go to higher temperature tool materials, and the containment blocks, right? Since they don't rotate, it's real easy to put active cooling on those, and that's what we've got in our next set of containment blocks that are being built, right, to help that heat. So I don't know actually how much higher you'd have to go on the containment blocks, because they've got active cooling passing through there all the time, very, very close to the containment walls themselves. So I think it's definitely possible, but it'll definitely take some work and some more R&D to make that commercially ready, I guess, right? But we just haven't tried out any of the high temperature tools at the moment, and the high temperature alloys, but it should.
Okay. Sorry guys if I'm butchering these acronyms and whatnot.
Right.
So next one, do these processes have MATIS or MATIS ratings or acceptable A basis allowables that other materials, properties, fatigue, etc.? Or is NASA accepting MUAs for these processes?
So these do not have MAPTIS processes, right? So we've been on with the single rod feeder, right? It's been really challenging to build the whole part, right? So we've just kind of been waiting, and we've been getting these parts machined and stuff, and we get ready to put on here. But we intend to start building up allowables, bases, once we get the continuous feeder on our PDS machine, and starting to build that up. And whether or not you could use it as an MUA, I guess that would be a question for the fracture control board, right? I would assume, right, if you had enough data to justify it, right, that they would go along with that for particular reasons, right? It's kind of situation specific, right? You'd have to look at it and see what it looked like. I don't know that I could answer that question 100%. You know, whether you could use an MUA, whether NASA would allow that for a particular NASA project. That would really be a Jonathan Burkholder type question within. You probably want to know the specific project, but we intend to start gathering allowable data very soon.
Okay, thank you. I think this will be the last question we have time for today. What is the contaminant plate material? Can it be changed for higher melting point materials?
Sure. Yeah. Actually, let me. Can I reshare my screen? Can we do a share thing where we can talk about the containment plates and what they are and how you change them out? Let me pull up Tech Topics presentation. We're going to talk about what the so this is a little newer picture, right? So you can see we kind of went from a block with the containment place was all one piece, and this is a three-piece block here with the liquid cooling channels in it. And if you go down here, so right, these are the two bottom pieces where everything's contained at, right? And you've got the coolant running through here. So you can really change, you know, you've got your bearings up above here, but you can really change this out to whatever you want it to be, right? So if you want to make it a different type of metal, if you want it to be, you know, tool steel, some type of stainless, some type of, you know, nickel alloy, or some kind of, you know, tungsten, ceramic, whatever you really want to do there, you can make these blocks into whatever, and they'll bolt on and off. We've really gone to a much more modular design with the newer iterations where we can change pin size, build height, and whatever, and then we're just machining. You know, if you want to change pin diameter, right, you've got to change both of these. But if you just want to change the exit geometry, right, it's just the bottom piece, right, and that's just a flat part. Pretty quick to machine, a really low cost to help just drive down the reduction in cost of the parts and up the versatility of the parts that you already have existing. So, but that's kind of, this is the Rev 2 of what's going on in here, right? We've got a bunch of different cooling channels running around here, keep everything cold so we can hopefully use cheaper, more conventional materials for higher temperature depositions, but also you can go to whatever material you want to make these out of. Should be fine. They're not difficult to machine or anything like that. There's no super complex geometries on there or anything like that. I think that was just a good visual, hopefully.
Thank you, Joseph. All right, if we did not get to your question today during the Q&A session, then we will follow up with you by email within the next couple of weeks. If you have any additional questions, please feel free to email them to us at the address on the screen, and we'll be sure to follow up with you guys. And once again, we appreciate you taking the time to be with us. Thank you all.